Okay, so I'm going to re-record this for a number of reasons. You never saw the first recording, so this is just the replacement for it. So we're going to take a look at 9.3 stoichiometry. So we saw the relationships between all of gases. Now we're going to look at the relationships between stoichiometry and gases and how we can determine those things. So molar mass and ideal gas law. So ideal gas can be rearranged to come up with molar mass. So again, we're going to start with the idea of PV equals nRT. So PV equals nRT. Again, this is kind of our standard equation. We need to know this equation because it is very powerful in kind of looking at these gas law situations or whenever there's a substance involved that is a gas. So we can rearrange it by plugging in molar mass. So let's take a look at molar mass. Molar mass, the units are in grams per mole. Grams is a mass, and moles, we use N typically for those things. And we see that we have in common, I have moles and moles there. Well, what this means is I can actually rearrange this equation and I can substitute in N. So let me rearrange my molar mass equation. N is equal to mass over molar mass. So now if I know the mass of a gas and I know what type of gas, I can also include that in there. So I'm going to take this and I'm going to substitute in. So N is equal to N. So I'm simply going to take this in and substitute it in, and we're going to get a new equation out. So we now have PV is equal to N, which is being replaced with mass over molar mass times RT. And so again, I'm just going to rearrange this, or I'm just going to write this out. So PV is equal to M RT all over molar mass. If I solve for molar mass, my final equation for this is molar mass is equal to MRT all over PV. So this is the final equation. This is going to allow us to calculate things based on their molar mass. So I said the type of gas doesn't matter, but it does when mass is involved in a handful of other things. So we're going to take a look at this in lab form. In fact, the second question, second or third question when we're looking at density actually is going to play into this. So molar mass is equal to mass times the ideal gas constant times temperature all over PV. And so with that, the units are going to work out and we're able to use molar mass. So if we take a look at this problem, how many grams of CO2 are in 15.0 liters of CO2 at standard temperature pressure? Right. So, we've got a handful of questions. Oh, I think they're different. Interesting. Okay. So I think that I have a couple versions of this, but in any event. So let's take a look. How many grams of CO2 are in 15 liters of CO2 at standard temperature pressure? Again, how many grams? So we're looking for mass. The CO2, we know that I'm going to have a molar mass of, and you can do it, you end up with 44.01 grams. And 15 liters, that is my volume. And now it's just a matter of plugging things in. So I'm going to rearrange this equation actually. So we end up with a mass time is equal to molar mass times PV all over RT. So my molar mass is 44.01 grams. My pressure is at standard temperature pressure. So my pressure is 1 atmosphere. My volume is 15.0 liters. My R is 0.08206 liter atmospheres per mole K. And my standard temperature is 273 Kelvin. And we plug this in and hopefully you're going to get a mass. I'll plug it in a little bit, but that's the idea. So same thing here, only we are again using the molar mass equation. Molar mass is equal to mass times RT all over PV. Can we figure out what the molar mass of this gas actually is? Same thing here. If we have 10 grams of hydrogen gas, how much does it weigh when it's at 50 Kelvin under a pressure of 1.54 atmospheres? So we're going to use the same exact equation. Again, sometimes the molar mass is hidden in what type of gas it actually is. So let's take a look at that. Good. So now let's take a look at that same exact equation and let's rearrange it again, or think about it in another form. So I have molar mass is equal to mass times RT all over PV. And now I'm looking for density. Well, density is equal to mass over volume. So essentially what I'm going to do is I'm going to rearrange this equation so it equals mass over volume. And I have them actually in the right spot right now. So what I'm going to do is all I'm going to do is I'm going to leave those alone and I'm going to move RT, basically just going to move RT and P over to the other side. So with that said, we rearrange this equation and what we end up with is molar mass times pressure all over RT is equal to mass over volume. So my density, this is my density equation. All of this is equal to density. So density is equal to molar mass times pressure over RT. Okay, so that's it. That's how we calculate this. Again, the density equation is giving us the density of the gas. So a couple things about this. Gases are typically reported in grams per liter. Liquids are typically reported in grams per milliliter. And then solids are typically reported in grams per centimeters cubed. So grams per milliliter is what we're going to use, or grams per liter is what we're going to use. Let me just correct this. So gas, liquid, solid. So gases are grams per liter. So although the numbers might be a little bit weird, you're going to have some answers that are rather large, but again, it's in grams per liter, which is very different than liquids, which is grams per milliliter. So don't be freaked out when you come up with that, when you see that. So what is the density of carbon tetrachloride? So again, we're going to start with the density. We're looking for the density, which is easy enough. So it's equal to molar mass times pressure all over RT. We have a pressure of 714 torr. We have a temperature of 125 degrees Celsius. We have R, which is a constant. So we got this. Again, I can just point out the fact that we have all of these things already here. So pressure we can take care of, temperature we can take care of, R we already have, molar mass, it's built into here, carbon tetrachloride, CCl4. So you should be able to come up with the density of this based on having all of that information. Okay, so pretty easy, straightforward. Again, it's just a derivation of the original equation. When we're in class, I'm going to kind of walk through how you can rearrange PV equals nRT. Next up. So this one's a little bit more complicated. This is exactly what the lab that we're going to do. So I'm going to kind of draw this out, but I'm going to let you guys work on it. So a large evacuated flask. So here's my large evacuated flask. Has a mass of 134. So the mass of this flask is equal to 134.567 grams. When the flask is filled with an unknown molar mass, with a gas of unknown molar mass to a pressure of 735 torr at 31 degrees Celsius, its mass is, so I've filled it with, so this is important. So what I've done is essentially, all right, that was the empty flask. So now what I've done is I've added a little bit of heat. That's heat. And I have filled it up with a gas. So we have filled it up with a gas. The only thing in there is the gas inside the container. It has some kind of little cap and we're going to see that. But ultimately I've added, so this is the mass of the flask plus the gas. And that mass turns out to be 137.456 grams. And so then I cool it down. And once I cool it down, we are going to take this last container. And when I cool it down, all of this gas condenses. So essentially I now have liquid gas molecules and I can weigh it. And that is ultimately actually how we got this mass right here it's actually the mass of this thing right here. So in fact, I probably should just move this over. So when I cool it down, that's what I have, mass of the flask and the gas. Assume the ideal gas equation applies, calculate the molar mass of this gas. So again, we're going to do the same exact concept. Molar mass is equal to mRT all over PV. Okay, so we need those terms in order to calculate this. So you need the mass of the gas, which we have, and the numbers I actually have right there, I've written out. We know R, we know the temperature, we know pressure, and the volume. The volume is going to be the difficult one. Look through that and try to decide what the volume is going to be, because I didn't tell you what type of evacuated flask, but I did give you enough information to figure out what the volume is. But yeah, so that's it. Again, density equation, molar mass equation, so you can actually calculate gases based on that. Next, let's take a look at gas pressure, gas mixtures and partial pressures. So before we kind of get down into the idea of partial pressures, let's talk about the idea of why we're interested in something called a partial pressure. So when we're talking about concentration, it is always kind of the part over the whole, or it's the solute over the solvent, right? That's typically solute over the solvent. And every single one of our calculations has this. So the concentration of, we have molarity, which is moles per liter. We have molality, which is moles per kilograms of solvent. We have percent by weight, which is mass over mass total times 100. And we have mole fraction. We're going to come back to mole fraction, but essentially it's moles over total moles. And that is our mole fraction. But all of these are the part over the whole. Gases are a little bit different. Gases, we don't typically ever talk about other things that are present because they don't interact. So we don't really care what the solvent is, and there's no solvent usually. So in air, color, yeah. In air, I'm going to have about 79% nitrogen and 21% oxygen about, and there's a bunch of other gases in there, but let's not worry about it. So 79% nitrogen, 21% oxygen. These right here are percentages, so that is a concentration. But typically what we do is we report in pressures. So when you have concentration, when we're talking about a gas, atmospheres is what we use, or pressures, I guess we should say, instead of atmospheres. It's not atmospheres, it's pressure. Is my gas, is my unit of concentration. So anytime you're talking about a gas, the amount of pressure something applies is the concentration. So pressure is now equal to concentration when we're talking about gases. So that 79% nitrogen is going to apply a certain pressure because it's part of it, and this one is going to apply it as well. And they're going to do it similarly based on how much is present. So that brings us to the idea of partial pressures. The pressure exerted by a particular component of a gas mixture. The Dalton's law of partial pressure basically says the total pressure of the mixture is equals the sum of the pressures of all of them. Sum of the pressures if it were alone. So P total is equal to the pressure of A plus the pressure of B. So if this were air we're talking about, the total pressure of the air exerting is pressure of the nitrogen, pressure of the oxygen, pressure of the CO2, so on and so forth. So this is a great demonstration of this. I have blue, red, and yellow gases. I'm going to combine together 300 kilopascals of the blue, 600 kilopascals of the red, 450 kilopascals of the yellow, and I end up with 350 or 1350 kilopascals total. It's all of the pressures combined. So what is the concentration of the blue? The concentration of the blue is 300 kilopascals. Again, pressure is equal to concentration. What is the concentration of the purple? 600 kilopascals. And the yellow the yellow is going to be 450 kilopascals. So again, those individual parts add up to be the total of 1350 kilopascals as the final concentration. So the addition of all of those is going to give us the total concentration. So what is the total pressure exerted by a mixture of 2 grams of hydrogen and 8 grams of nitrogen at 273 in a 10-liter vessel? So when we're trying to figure this out, we're doing the same thing where we're trying to figure out these individual pressures. So with that said, I'm going to ignore the nitrogen for now, and I'm going to look at just the hydrogen. So if we look at H2 gas, can we calculate the pressure involved here? So what is the pressure that it exerts? So PV equals nRT. I want to solve for the pressure of H2, which is equal to the moles of H2 times R times T all over the volume. How many moles of H2 do I have? And I'm actually just going to do this. Well, I guess I can do it up here. So I have 2 grams. In this case, I'm actually given a mass, 2 grams of H2, grams per mole. Because it's H2, 1 mole is equivalent to about 2 grams. So this is equal to 1 mole of H2. Okay, great. So we end up with 1 mole of H2, R 0.08206 liter atmospheres per mole K. And my temperature was 273 Kelvin, and my volume is a 10-liter vessel. So if we do these calculations, let's see here. So 0.08206 times 273 divided by 10 gives me 2.24. And then what's my unit? Let's take a look. Moles cancels, Kelvin cancels, liters cancels. We're left with atmospheres. So that's part of it. So that is my pressure exerted by the hydrogen. And so now we need to take a look at, well, what is the pressure exerted by the nitrogen? So the nitrogen gas, we're going to do the same exact thing, PV equals nRT. We're going to substitute those in, and I'll let you guys solve this. But ultimately, it becomes the total pressure is equal to the pressure of the hydrogen plus the pressure of the nitrogen. So that means I've already got the 2.24 atmospheres plus whatever you guys get for that is going to equal my total pressure. Okay, so that's Dalton's law. Partial pressure is basically just saying we combine all of the parts, and that's the total pressure. Sometimes we're not given, sometimes we're just given a little bit of information. And so another way to look at it is by the idea of mole fraction, because again, we converted to moles up here. Because we're converting to moles, moles are important in terms of quantity. Again, the type of gas does not matter, but the number of moles will. So partial pressure and mole fraction. So another way of looking at it is this actually Raoult's law is what it's called, but the idea of mole fraction. So the pressure of an individual substance, A in this case, gas A, is equal to the mole fraction times the total pressure. Okay, so the percentage or the mole fraction of the portion of moles of gas is going to be equivalent to the total pressure. They're going to be proportional to the total pressure. So I would like to point out the fact that if I have just pure something, so if I have, let's say, pure substance A, okay, so if I have 100% gas A, okay, what that ultimately means is there's no mixture here. It's the same thing. The pressure of A is equal to the mole fraction of A times the total pressure. Well, turns out that when this is true, the mole fraction is equal to 1, and therefore pressure of A equals the total pressure, right? So that is how Raoult's law works. If I have 50% A and 50% B, now that mole fraction is going to drop by half, and I actually have to do a calculation at that point. So again, mole fraction is equal to the moles of A over the total moles present. Okay, good. So A mixture of 40 grams of oxygen and 40 grams of helium has a total pressure. So in this case, I've got a total pressure of 0.9 atmospheres. What is the partial pressure of O2 and H helium? I can't use the same thing that I just did because I'm not given a pressure, I'm not given a volume, I'm not given temperature, I'm not given any of that. But we can use this idea of partial pressures or mole fraction. So let's figure out the mole fraction for oxygen. So if we take a look at oxygen, the mole fraction of oxygen is going to equal what? Well, we have to convert these to moles. So if I have 40 grams of O2, and I'm actually just going to write out the generic version of it. We're going to do it in class. So the moles of O2 over the moles of O2 plus moles of helium. And that's going to give me mole fraction. And so once I have mole fraction, then I can substitute it in. So the pressure of O2 is equivalent to the mole fraction of O2, which you just calculated, hopefully, times that total pressure. And we know that. So the mole fraction, which you're going to figure out right here, times total pressure, which is 0.900 atmospheres. So what portion of it is O2? And by the way, you can always, the rest has to be the other gas. So you can do that calculation. I encourage you to do the other calculation the same way, but we can also say, well, if you know one, then you know the other one because it's just the rest of it. Good. Okay. And so same kind of question here. What are the molar ratios, or what are the partial pressures of each of those gases? The total pressure is 3.5. And that is it. So perfect.